Molecules take very intriguing forms, at times looking like something taken from Caillou's drawing book, like the impressive Canatex propylene we covered previously. There are also awesome smaller molecules that make chemists wonder about effects and limits of ring strain. Most of you will know Cubane, the literal molecular cube. And scientists recently reported the synthesis and characterization of Azahomocubane, one of hopefully many more Cubane analogues to come. Today we'll start with a truly elegant old-school synthesis of simple Cubane, and then dive into Azahomocubane's modern synthesis and interesting properties. Doing so, we'll also learn how people make the absolutely mad octanitrocubane, how chemists can use the unstable anti-aromatic cyclobutadiene as a reaction partner, why azide groups are very useful for rearrangement reactions, and last, why you should never throw away your old products. As always, the nerds will be able to geek out on hyperhomodesmotic reactions and second-order perturbation theory, but I will save this for last so that mortals can flee ahead of time. Have you smashed too many glass speakers recently? Or have you ever spilled some acid on yourself, only wishing you had noticed earlier? Cell Supplies, a small company actively supporting amateur scientists, is offering my viewers a 15% discount on their already very affordable and high-quality glassware. They also have hardware equipment and a unique indicator lab coat that changes color when exposed to acids or bases. This can be helpful to detect spills or simply function as a swaggy fashion statement. With the discount code, you're bound to get a great deal, so if you are frequently ordering equipment, which might be up to 30% of you, check out Cell Supplies. Hard to believe, but Cubane was first synthesized already in 1964. Although a pioneering piece of work, the synthesis is a bit long, so we will not dissect it here. We are after something much shorter. There are some other YouTube videos you can check out if you're interested in the experimentals of this one. Notably, Philip Eaton, part of the first Cubane synthesis, continued to be a driving force of Cubane research and almost 4 decades later also led the first synthesis of octanitrocubane. As you can imagine, this required some unpleasant reaction conditions, and of course, this thing goes boom. The introduction of nitro groups worked via so-called interfacial nitration of a cubyl anion at the melting interface of frozen THF and N2O4. I'll gladly pass on this. Also, the last step requires you to think, yes, let's do an ozonolysis of a nitrosyl heptanitrocubane. No, thank you. Octanitrocubane was hypothesized to be a potentially best-in-class non-nuclear explosive based on theory, but its experimental density was shown to be lower than predicted. There are no public records of larger-scale synthesis and testing, so it's just research from a computational point and remains elusive. Back to normal Cubane, mind-blowingly, just after 2 years, an incredibly efficient synthesis was published. It uses cyclobutadiene as a starting material, which seems crazy but also very logical given Cubane is full of squares. You will know that this is an anti-aromatic compound and very unstable, so it's not possible to store it in a bottle. However, oxidizing this iron complex, which can be handled better, leads to the release of cyclobutadiene within the reaction vessel. In this case, allowing for a 4+2 cycle addition with this diketone, which bears 2 bromo groups and another olefin, both essential to this efficient synthesis. After the endo-cycle addition, the 2 double bonds are well positioned to engage in a 2+2 photo addition, obviously one of the key reactions available for construction of cyclobutane rings. Now we have this basket-like intermediate which can undergo a base-mediated double Favorsky reaction, leading to ring contraction of the cyclopentane rings. This creates the Cubane system, and now you can simply remove the acid groups in some steps via decarboxylation. The yields are suspiciously consistent at 80%, but even if they would be lower, it would not take away from the nice sequence and use of cyclobutadiene. Very timely, there was a super recent publication on another metal-free way to liberate cyclobutadiene. Quite nice work and much better than creating some toxic iron compounds. As kind of a common theme in this video, this works via a retro 2+2 addition to release nitrogen and create reactive cyclobutadiene in the process. Before we continue, I wanted to thank the 3 mad lads who signed up to my channel membership so far. If you also like these videos and want to see more of them in future, please consider becoming a channel member. So the little Cubane boy is done, but how do we create a much more complicated Azahomocubane? Well, a logical intermediate would be a simple Cubane amine. Because it's not 1964 anymore, we don't have to create Cubanes bottom up. Rather, we can simply buy them because there are crazy folks performing Cubane synthesis on kilo scale. This diester Cubane is not cheap, and although it comes with the Cubane, it also has 2 esters. Because we need the mono-substituted aminocubane, we need to get rid of one of them. This is achieved via hydrolysis with just one equivalent of hydroxide and subsequent Barton decarboxylation of the activated acid. So how do we get the amine from the ester? After hydrolysis, the acid was converted to the acyl azide. This prepares the courteous rearrangement, which is facilitated by the strong energy gain of N2 release. The intermediate isocyanate can be trapped with various nucleophiles, in this case with terbutanol to give the N-Boc carbamate product. Simple acidic exposure releases the cubyl amine. What now? It's azide time again. Exposure to triflyl azide, a terrifyingly reactive azide transfer reagent, creates cubyl azide via substitution. Both of these azides come with a hefty explosion warning, so they are best handled only on solution and behind the blast shield. Adding some acid now, you guessed it, leads to another courteous-like rearrangement with migration of the alkyl rest to displace N2. The resulting carbocation is then trapped by the acetic acid in the environment to give the product. After all of this, we finally have a single nitrogen in the correct oxidation state installed. Because we need the nitrogen in a corner position, there is more to be done. Once again, let's do a sweet rearrangement. N-chlorination creates the opportunity for a new CN bond formation, initiated by the fragmentation of the acetate. This is reminiscent of the Favorsky ring contraction we saw in normal Cubane synthesis, just this time the halogen-leaving group is bound to nitrogen. The intermediary amide can be hydrolyzed and voila, we have finally positioned nitrogen in a cyclobutane. Now we just need to create the final linkage of the extra carbon and nitrogen. We have the ester carbon to work with, so the final steps use the methyl ester. Now it's just a simple sequence of ester reduction, chlorination, and intramolecular SN2 to get to Azahomocubane. As this final product is volatile, they prepared the salt form for easier handling. So does Azahomocubane explode like octanitrocubane? Clearly not. Just because it looks strained does not mean it can rapidly release nitrogen, CO2 or other things as part of an explosion. Its decomposition is much less exciting actually. Exposure to acid or simple storage in the refrigerator leads to ring opening of the cubane. This step is irreversible, a testament to the high instability of Azahomocubane. It also makes you think that the last SN2 reaction with the primary leaving group is probably one of the only reasonable ways to install the system in the first place. In terms of geometry, the team obviously expected the product to be different than your generic tertiary amine. DFT calculations indicated that this was definitely less than ideal sp3 geometry. And the crystal structure, funnily found via serendipitous discovery after many months, was consistent with this. You can see that the 5-membered ring distorts the picture quite a bit, so homocubanes look more like baskets or houses instead of cubes, if that makes sense. What is the impact on basicity? In this table you see a comparison of strained tertiary amines. The Azahomocubane nitrogen is quite pissed, with strain energy being an order of magnitude higher, but this means that basicity is actually more than 10-fold lower. You might think that because there is more strain, the nitrogen might be happier in some other configuration, but looking at nitrogen NMR chemical shift showed that the nitrogen in Azahomocubane is less electron-rich compared to the other frameworks, which aligns well with the observed basicity trend. Notably, the hypothetical Azahocubane has 45 kilocalories per mole more strain energy than Azahomocubane, which makes you wonder how long it will take to synthesize it in the lab. Finally, they looked into hypothetical atom exchange and hypohomodesmotic reaction calculations. What is that? It's basically a nerdy theory crafting method of computing bond separation and formation energies, and the name is due to different sets of reaction conditions qualifying for different reaction types. For example, the hypohomodesmotic reactions shown here can be used to compute strain in cycloalkanes. Basically, you're taking heats of formation of the individual molecules, which can be computed or are known values, and figure out what is the enthalpy value Q needed to balance out the hypothetical reaction. You can see that while cyclohexane has a Q of almost 0 because it is not strained at all, the Q value is much higher for cyclopentane, butane, and propane as their strain increases. Applying this methodology to our question, we see that Azahomocubane is significantly more stable than the all-carbon homocubane. But why is that? To shed some light on this, they modeled nitrogen lone pair sigma star interactions with the carbon framework. This revealed that there is substantial hyperconjugation from the nitrogen with both adjacent cubic and basket handle CC bonds, somewhat stabilizing the system compared to normal homocubane. This was confusing as heck, by the way, as the table the authors provided was suggesting there was a C11 and C15, which does not make sense. And it's probably just these interactions here. In any case, it is evident that there are both hyperconjugative effects and general orbital reconfiguration at play. For example, the highlighted Benz rule describes orbital reorientation once you add in a more electronegative substituent like fluorine or nitrogen. In such settings, orbitals with S character are pointed towards more electropositive substituents like hydrogen or carbon, so this leads to some changes in bond geometry and lengths. This work doesn't answer all of our questions, but it shows that Aza variants of strained systems will be an interesting playground for chemists. If you like this video, please subscribe, leave a comment, activate notifications, and consider becoming a channel member. And if you run a lab, consider checking if Cell Supplies has a good deal in store for you. Thank you, and as always, until next time.